Welcome back to our geometry series. Today we are up to section 5.6 where we will be looking at trigonometric ratios. Here's our good friend, a right triangle. It happens to be a 30, 60, 90 triangle. Let's pretend that the length of this leg, CB, is 1. Thanks to theorem 67, we know that the hypotenuse, AB, is twice the length, and the other leg is root 3 times the length of that first leg, so just root 3. Here we have a similar triangle. It's bigger, but the angle measurements are the same. So that's what we call a similar triangle, DEF. Still a 30, 60, 90 triangle. So let's say that segment FE has a length of 1.5. Again, using theorem 67, we know that the hypotenuse, DE, is twice the length, so it becomes 3, and the other leg, DF, is 1.5 times the square root of 3. Let's focus on this 30-degree angle in both triangles. And I want to look at the ratio of the length of the opposite side over the length of the hypotenuse. So the opposite side of the 30-degree angle here would be segment FE. This leg is 1.5 long. The length of the hypotenuse is 3. So we write that as a ratio, or a fraction, 1.5 over 3, which turns out to be 0.5. If we look at the original triangle, we take that length of the opposite side, CB, and put it in the ratio over the length of the hypotenuse, and we get 1/2, which is also 0.5. For any right triangle, this ratio for the 30-degree angle will always be 0.5. So this is true for any similar triangles, regardless of how big it is. When we take the ratio of the length of the opposite side of an angle over the length of the hypotenuse, this is called sine. So the sine of 30 degrees is 0.5. Mathematically, we would write it like this. We use a 3-letter symbol, SIN, for sine. So the sine of 30 is equal to 0.5. This is true for all right triangles that contain a 30-degree angle. So what is the sine of 60 in this triangle? Again, we want to take the length of the opposite side over the length of the hypotenuse. So that length is root 3 over 2. Now here we'll need Mr. Calculator, and it comes out to about 0.866. Now let's look at a slightly different triangle, still focusing on angle A, but this time I want to look at the length of the adjacent side over the length of the hypotenuse. This is what we call cosine. If we add some lengths to the sides of the triangle, we can ask, what is the cosine of A? As you can see here, we use a 3-letter symbol, COS, as shorthand for cosine. So what is the cosine of A? It's the adjacent length over the hypotenuse length. So that would be 4 over 5. So the cosine of A is 0.8. What about the sine of angle B? Since we're looking at the sine of B, we need the opposite side over the hypotenuse, which is 4 over 5, which gives us 0.8. This is not a coincidence. The cosine of one angle will always be the sine of the other angle in a right triangle. Finally, let's look at one more relationship. Still talking about angle A, let's look at the length of the opposite side over the length of the adjacent side. This is what we call tangent. So, what is the tangent of A? Here, we use the letters TAN for shorthand to ask what is the tangent. So, tangent of A would be the length of the opposite side, which is 3, over the length of the adjacent side, which is 4. So the tangent of A equals 0.75. Now let's take a look at this triangle. We've been given the length of the hypotenuse and one of the legs, but none of the angles. The question here is, what is the measurement of angle B? Well, we know that the sine of B will equal the length of the opposite side over the hypotenuse. So that is 6 over 23. And that gives us roughly 0.2609. But what do we do with that information? How does that help us find the measurement of angle B? Well, you could go into your computer and find a scientific calculator, but we're going to use a trigonometric table. Most likely, this is in the back of your textbook, but can easily be found online. Here's a section of the table of trigonometric ratios. This link will also be provided in the video description. So we know the sine of B of that triangle was around 0.2609. So let's look in this column labeled sine. So down here, we see 0.2588. That's pretty close to 0.2609. So we know that B is a 15-degree angle, or thereabouts. So we solved the answer. The measurement angle B is approximately 15 degrees, thanks to the trigonometric table. In some math classes, you may say this, S-O-H-C-A-H-T-O-A, SOHCAHTOA. This is a handy mnemonic for remembering how these ratios interact with each other. Sine is the opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is the opposite over the adjacent. SOHCAHTOA. Let's jump to the whiteboard and do some examples. Okay, I'm going to draw a triangle, something like this. That's not great. Okay, here's our right angle, point A, B, and C. B is our right angle, and let's give it some side lengths. We're going to say that this is 8, this is 17. We'll make that a better 8, 8, and this is 15. So here's another 3 whole number triangle, like a 3, 4, 5, or a 5, 12, 13, 8, 15, 17. So let's find the sine of A, the sine of C, the cosine of A, the cosine of C, and we'll do our tangents down here, tangent A and tangent of C. So remember, the sine of something, I'm just going to write down here, sine is the opposite over the hypotenuse. All right, so let's do that over here. Sine of A. A. What is opposite of A? It's 15. Equal, 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 equal. So this is 15 over the hypotenuse, just this guy, 17. Sine of C, again, the opposite of C is 8, so it's going to be 8 over hypotenuse. And cosine. Cosine is the adjacent over hypotenuse. And I think of it like like when you cosine something, it's two people and they're together. So when you cosine of A, you're interested in the leg that's touching A. So the cosine of A would be the adjacent length, which is 8, over the hypotenuse, which is 17. And the cosine of C is the adjacent leg, 15 over the hypotenuse, 17. That's a 5. And like we saw on the slides, the sine of one and the cosine of the other are going to be equal. 15 over 17, 15 over 17. See how that happens? These are complementary angles to each other in this trigonometric world. And then finally, the tangent is the opposite over the adjacent. So, SOHCAHTOA, right? S-O-H-C-A-H-T-O-A, TOA. So tangent of A is the opposite, which is 15, over the adjacent, which is 8. And the tangent of C, again, the opposite is 8, and the adjacent is 15. So you can see when you take the tangent of the two angles, they end up being the reciprocals of each other. Let's clean this off and do another example. Okay, we're going to draw another triangle, something like that. We're going to put our right triangle here, and we're going to mark this. I'm still on the thingy here. E, F, and D. And we'll put some information. We'll say this is 5, and this is 13. What we want to know is, what is the measurement of angle E? What is the measurement of angle D? And what is the length of the side EF? So we've got three things we're trying to figure out here. Now we've been given some information. We have a leg and we have the hypotenuse. So let's look at E relative to these two sides. Because we know the opposite and we know the hypotenuse, we can say that the sine of E will be equal to the opposite over the adjacent, or opposite over the hypotenuse, 5 over 13. Yep, 5 over 13. And if you use Mr. Calculator, that ends up being 0.3846 and a bunch of other stuff. And if you pull up a trigonometric table and you go into the sine column and you go all the way down to the closest number to this, and we see that this is pretty close to 22 degrees. So we can say that E is roughly 22 degrees. Now because we know, let's just call this 22 degrees, and this is 90, we could do some basic math to figure out what this is, but let's use some trigonometry because that's more fun. But we can say that the cosine of D cosine, again it's the one that's right next to it when you use a cosine, is adjacent over hypotenuse. So it's the same fraction, 5 over 13, which again equals about 3.846. If we go to this cosine section of the table and go all the way down till we find 3.846, we get roughly 68 degrees, which kind of makes sense. So this is roughly 68 degrees. 68. And again, 68 plus 22 would give us 80, 90. We still have this length to try to figure out. We could use any number of trigonometric ratios. Let's use tangent. We haven't done that yet. And we're going to talk about D here. This marker is kind of dying. So we know that the tangent of D is going to equal the opposite over the adjacent. So that's opposite over adjacent. The opposite is the mystery, right? It's EF. We don't know what it's going to be. It's this thing over 5. But we already know what D is. So I'm going to rewrite this a little differently. I'm going to say that the tangent of 68 is equal to EF over 5. Now, using some algebra skills, we can take this 5, multiply both sides by 5. It'll cancel out over here. And we can rewrite this down here somewhere as 5 times the tangent of 68 equals EF. I'm going to rewrite this here. If you go into your trigonometric tables, you'll see that the tangent of 68 is 2.4751. So this is 5 times 2.4751. All I did was look up tangent of 68 in the table, and it's 2.4751. We got to multiply by 5. That gets us 12.3755. So we can put that up here, 12.3755. Now you may notice something. If this was 5 and this was 13, and we got all Pythagoras back in here, we'd end up with exactly 12. But we got this weird number of 12.3755. Well, what happened here? Well, because we're dealing with these weird decimal places that actually go out for, forever and forever, and this decimal place goes around forever, all these rounding errors have caused us to come up with an answer that isn't completely right. But when we had estimates here, so these all should be like, ish. So 12.3755, that's kind of 12, depending on how you look at it. But you can see how we got sort of the right answer, but we're using estimates for all of these ratios and fractions and stuff. So today we talked about sine, cosine, and tangent, the main trigonometric functions when it comes to right triangles. In trigonometry, you're going to spend a lot more time with this stuff, but in geometry, this is all we're going to cover going forward. And that's it for today. We'll see you next time.